Here we're going to look at some limits at infinity of some more complex functions, but before we do that, I want to talk about this theorem because it's going to come in handy for us here. It says the limit of a polynomial function at infinity. So this is only going to work if our limit is at either positive infinity or negative infinity. This is the only time we can use this rule. So we can find the limit of a polynomial function at infinity. It is the same as the limit of its leading term at infinity. Be careful here. The leading term is not necessarily the first term. The leading term is the term with the highest degree. And the highest degree really means the highest power of our variable. So what we can do in these examples, we're going to look at the limit of these functions as x approaches positive and negative infinity. So for first up, we've got p of x equals 2x cubed minus x squared minus 7x plus 3. Now, without this theorem, we might end up in situations where if we try to kind of quote-unquote plug in infinity, we might end up with situations where we end up with something like infinity minus infinity. Now, infinity is not a real number. It doesn't always play by the same rules as real numbers. So if you asked me what infinity minus infinity was, I could not give you a definite answer. It might be infinity. It might be 0, it might be of some other finite number, it might be negative infinity. There's no way to know without having more information. So this theorem is going to really help us. So if I want to look at the limit as x approaches infinity of this function, p of x, here we've got 2x cubed minus x squared minus 7x plus 3. So I get to look at this limit and I say, hey, it's the same as the limit of its leading term. So I'm going to identify the leading term here, which in this case, the term with the highest degree or the highest power of our variable is 2x cubed. That's all I need to pay attention to. So I can actually just look at the limit as x approaches infinity of 2x to the third. And I can sort of ignore everything else. I can just kind of almost chop off the rest of this problem. For the rest of this problem, for this limit, it doesn't matter. We just need to look at that 2x cubed. What I would recommend doing after this, if you have a coefficient in front of your variable, I would factor that to the front of your limit. I would say this is 2 times the limit as x approaches infinity of x cubed. My goal here in doing that is just to make that inside part as simple as possible because I kind of know what x cubed looks like. So since we know what the graph of x cubed looks like, or if we don't, you can kind of draw a quick picture and say, okay, we want to know as x approaches infinity, so we're talking about the right end behavior. What is our graph doing as we move to the right? What y value are we approaching? Well, in this case, that's going up and up and up and up, so we're approaching positive infinity. So here we've got 2 times positive infinity. Now, I said earlier that infinity doesn't always play by the same rules as real numbers, but it does follow some of the same rules. So in this case, we can just kind of look at the sign here, and that's really what I'm worried about, is are we going to multiply by a negative number? Because that would change the sign here. In this case, though, we have a positive 2 times a positive infinity. We're still going to get back positive infinity then, and there's our limit. If I wanted to look at the limit as x approaches negative infinity of this function, of our function p of x, we can do the same thing here in this case. Well, we can say, all right, well, that's the same as the limit as x approaches negative infinity of just our leading term, which we said was 2x cubed. And then, okay, just like last time, I would factor out that 2. So we've got 2 times the limit as x approaches negative infinity of x cubed. And now I can just look at this part. I'll worry about the 2 in just a moment, but I'm just going to look at that part. So this time, I'm asking as x approaches negative infinity, so as I move to the left, what's my y value doing? Well, it's going down, it's decreasing. We would say it's going to negative infinity. So we have 2 times negative infinity. So we have a positive number times a negative infinity. A positive times a negative, that would give me negative infinity. So really it's just the sign that I care about. If I did have a negative number right here, it would have changed the sign. And we'll see that in the next example here. So this is a really nice theorem. It allows us to just pick out the term with the highest degree and only look at that. It simplifies our problem a whole lot. Let's look at one more example here. This time I've got f of x equals negative 5x to the 5th power minus 3x to the 6th power minus 6x plus 1. Be careful with this one. I've intentionally written it in a little bit of a tricky way here. Remember the leading term is not always going to be the first term. It is the term with the highest degree, the term with our highest power of our exponent. So our leading term for this problem will be negative 3x to the 6th power. So if I wanted to find the limit as x approaches infinity, if I just said, hey, find the limit as x approaches infinity of our whole function, negative 5x to the 5th minus 3x to the 6th minus 6x plus 1, we'll start by identifying our leading term, which in this case is negative 3x to the 6th. It's really important that we grab that negative sign there too. We do want to make sure we grab that. And we could ignore everything else. So this is the same as saying limit as x approaches infinity, negative 3x to the 6th power. In this case, just like last time, if we have a coefficient, I would go ahead and factor that out. So I'm going to factor the negative 3. I'll say negative 3 times the limit as x approaches infinity of x to the 6th power, because this is a whole lot easier to look at, I think. Now, x to the 6th, that's not a function that maybe we know backwards and forwards, like maybe x squared or x cubed, but what I can do is I can look at the power and I can say, okay, x to the 6th, that is an even power. An even power is going to have the same end behavior as x squared. If I was to look at the graph of x to the 6th and the graph of x squared, the end behavior, what it does on the right side and the left side, is going to be really, really similar. So I can kind of use that as a substitute here. And I can say, okay, as x is approaching positive infinity, so as we move to the right, I'll look at my graph and say, okay, well, the y value is going up. It's increasing. My y value is approaching positive infinity. So here we have negative 3 times positive infinity. But when I multiply these two now, here I've got a negative 3 times a positive infinity. Well, 3 times infinity I know is still going to be infinity, still going to be, you know, an incredibly large number, one that we can't understand. But when I multiply by a negative, it will change the sign. So when I take negative 3 times positive infinity, I'm going to get back a negative infinity. And then lastly, then we'll look at the left end behavior too. We'll say limit as x approaches negative infinity. Again, we could write out this whole function, but we know that it's just that negative 3x to the 6th. That's the important part. So I want to look at the limit as x approaches negative infinity of negative 3x to the 6th power. We'll factor out the negative 3. So we've got negative 3 times the limit as x approaches negative infinity of x to the 6th. So now we're just looking at the limit as x approaches negative infinity of x to the 6th. Well, we've got that graph up here in red. Since we're approaching negative infinity, we're looking at the left side. So again, the y value is increasing. The y value is approaching positive infinity. So we end up with negative 3 times positive infinity. When I multiply those two, I end up with negative infinity. So this is a really, really nice property that we get to use for polynomials. And again, one thing that I just really, really want to stress is that this only works at infinity. If we're approaching any finite value, if we're approaching 4 or 5 or -2, then this theorem won't work. It only works if we're looking at a limit as x approaches positive infinity or negative infinity.